So yesterday we talked about forming the hypotheses. We didn't really test them, we just formed them. Today we're still not going to test them, but we're going to talk about the errors that we could have from testing. Make sure you get your notes out. It's still, I feel like today's still a pretty easy day. I know I said it was short, but I feel like short doesn't necessarily mean easy. It can be short, but then be really, really complicated. Today's not as easy as yesterday was. You have to think a little bit more today, but it's still not bad. So the way to think of an error and hypothesis testing, that would be like, think of it like you're doing a science experiment and you want this, you're watching the experiment and you're like, oh yeah, it's getting colder. The temperature is getting colder on the beaker. And you're not even touching it. I mean, somebody comes by and touches it and it's not getting colder, it's getting hotter. You would be in error, right? You'd be mistaken saying it's getting colder without even touching it. It's really getting hotter. Exactly. That example, but just go with it. Or a better example would be you get a COVID vaccine. They're like, oh yeah, it's working. This vaccine works. And then you still feel miserable the whole time. You don't get any better. Chances are it's probably an error. Probably doesn't really work. Okay, so when we perform these hypothesis tests, I want to go next. There we go. We have two decisions. We can reject the null, or we can fail to reject the null. Those are our two decisions that we talked about yesterday. When we make one of these decisions, there's the possibility that you could be wrong. Or that you made an error. That's just, honestly, the fact of life. Anything you do could actually be the wrong thing. So each could possibly be a wrong decision. Therefore, we have two types of errors. We could have a wrong decision here where we need to reject H naught, but we don't. There it is. So we need to reject it, but we don't, or vice versa. We need to fail to reject, but then we conclude that we reject it. So it could go either way. Yep. Would it help if, is that ice in that bag?
Yes, sir.
Would it help if I put a towel in under it so it won't get your notes?
What? Oh, I got saran wrap on, so it's my notes. I'm about to pick it up.
Oh, okay, perfect. You're welcome. I just didn't want you to get your notes all wet.
Yeah, I saw it. I'll take it off.
Okay.
It's been. Start over to it out.
Okay, Okay, so we have a type 1 error. That's the first kind we're going to talk about. That's the error of rejecting the null when it's actually true. And remember here, when this, I say remember, for this section, when I say the null is true, remember to kind of take that with a grain of salt. Like we said yesterday, always be suspicious, always be suspect. So we're saying it's true today, but really that just means we don't have enough evidence to say it's false.
Actually, it's true.
I mean, it could be. If your, for instance, if your population mean is exactly that on the dot, 8,000 for instance, on the dot, then for the probability, we're going to learn some more of the Greek alphabet. As if we haven't learned enough already, let's learn some more Greek letters. The probability of the type 1 error is denoted by alpha. So this is the lowercase alpha. This is called the significance level of the test. So earlier this semester when we kept saying things like it's statistically significant, that's going to take kind of a whole new meaning once we get through with hypothesis testing. So if we had a test where alpha is equal to 0.01, it's said to have a level of significance of 0.01 or to be a level 0.01 test. That's type 1 error. Then we have the type 2 error. So that's failing to reject the null when the null is actually false. We fail to reject when we should have. So the probability of the type 2 error is denoted by beta. We learned 2 new Greek letters today, alpha and beta. Go back. Okay, so let's look at this table. Another way to look at these is in this table form. So on top we have the actual values of the null. On the side, that's our decision. But let's think of the one that's on the bottom left. Let's suppose the null is true and we fail to reject it. What kind of decision was made? Did we make a good decision or a bad one? It's true and we fail to reject. That's good. That's what we want to do if it's true.
Because if it's right, you wouldn't reject it.
That's right. Now let's suppose the null is true and we reject it. Not good. What kind of error is it? Type 1 or type 2?
Type 1.
Type 1. So when the null is true and then we turn around and we reject it, that's a type 1 error. Now let's go to the next box. When the null is false and we reject it, what kind of decision was that? That's the correct decision. And then the last one, the null is false, and we fail to reject it. Type 2 error. So to kind of make an analogy with these to really be able to better understand them, let's look at a medical test. And since we're dealing with COVID, and everybody's talking about COVID, let's just kind of tie it to that. So let's say the null hypothesis is that the patient has COVID. So the specific disease we're going to use, let's just use COVID. The patient has it, that's the null. The alternative is that the patient does not have COVID. And then the type 1 error would be equivalent to a false negative. That'd be like saying the patient does not have COVID when they actually do. Okay, there's an imposter among us.
Okay, you made a moment references. You played with this. Okay. Ryan Schultz. You downloaded Among Us on the computer and played with this?
No.
Go with
The type 2 error is equivalent to a false positive. So that's saying the patient has COVID when they don't. You're in quarantine for 10 days, but you're perfectly healthy.
What happens when you go to a nurse and say you're say you're research or something like that?
And then there's one picture that I remember from statistics when I first took it in college. And then I took another statistics class and they brought the picture up. And in grad school, they brought the picture up again. But evidently, it's just a really popular one when you're talking about types of error. So, even though it wasn't in the PowerPoint, I had to make sure I included it. A type 1 error would be like a guy going to the doctor and being told he's pregnant. And I don't know if you can see it, but to me the look on his face is priceless. What the? Okay. And a type 2 error would be a woman that's clearly pregnant being told you're not pregnant.
Not in the episode.
So that's, like I said, that one's been around for a while now. When I was doing the notes, I saw that. I'm like, that's that picture. I gotta find it. And like I said, the main thing that sticks with me is the guy's look. Not really so much females, just his look. Like, anyways. Let's look at an example. So the U.S. Bureau of Transportation Statistics reports that for 2009, 72% of all domestic passenger flights arrived on time. Now, what they're calling on time is within 15 minutes of the true arrival time, the scheduled arrival time. The true time is within 15 minutes. Suppose that an airline with a poor on-time record decides to offer its employees a bonus if, in an upcoming month, the airline's proportion of on-time flights exceeds the overall 2009 industry rate of 0.72. So what would our null hypotheses be here? Or I shouldn't say the null. Be both, the null and the alternative.
Where's null again?
It's equal to 47.
So for AP, it'd be P, not mean. P is equal to 0.72. So the null hypothesis is what we're wanting to test.
Okay. It's different for AP and dual credit?
Because dual credit, really, you go based on the alternative for the most part, and that kind of determines the null. Now the problem itself tends to determine the alternative. So the problem says that we exceed 0.72. So our alternative would be that P is greater than 0.72.
Still the AP one. Oh, that's the same one for everyone.
Yeah, this one's the same for all of us.
But the HO is.
Yeah. This one for dual credit should be less than or equal to 0.72.
But in AP it's just equal.
And AP is just equal to, that's right.
And the P is it a lowercase or uppercase?
Lowercase.
Because the big P is probability. What does little p mean? Okay.
Population proportion.
I kind of blanked out for a second. I just had to read that.
Yeah.
Thank you.
Those are our null and alternative. Okay, what would a type 1 error be in this context?
Type 1 error?
Yes.
The study reports that P is greater than 72, but does forgiveness.
That's right. So the company could come back and give their employees the reward, the bonus, but then they didn't make a proportion that's greater than 0.72. So they have less than 72% of their flights on time. And they still got the reward. That's a type 1 error. They didn't meet their goal, but they still got rewarded for it.
Wait, I thought HO was when it's like 6 feet. Yeah, I thought HO was when like the first one succeeds and then the second one doesn't gets rejected.
Yeah, type 1.
Yeah.
Type 1 error is the error of rejecting H naught. So it's the error of rejecting this one when, or in y'all's case, this one. We reject it when it's actually true. So it's actually true here. P is less than 0.2, but we reject it in favor of this one.
Okay.
That make sense?
Yes, sir. I got you.
What would a type 2 error be in the context of the problem?
We don't get the bonus, but they should.
That's right. Type 2 error is when they do not receive the bonus, but they deserve it.
So that's when they got it right, but they still didn't give them one. Okay.
Questions on this one? I see some trying to write it down, so I'll slow my roll.
What are you drinking, Mr. Short?
It's like a lemon lime supplement that I mix with water.
I got you.
Anyone still trying to get it written down? Okay. Next one. So in 2004, Vertex Pharmaceuticals, a biotech company, issued a press release announcing that it had filed an application with the FDA to begin clinical trials on an experimental drug that had been found to reduce the growth rate of pancreatic and colon cancer tumors in animal studies. So, data resulting from the planned clinical trials can be used to test. Well, first we have to identify what we're testing. Mu is the mean growth rate, true mean growth rate of tumors for patients taking the drug. So our null would be that mu is equal to the mean growth of tumors of patients who are not taking it. So our null will basically be saying you have that. Or if you're in credit, the mean growth rate of those not taking it will be greater than or equal to. The alternative is what we want. That's kind of what we're hoping to find. That's that the true mean growth rate of those taking it is less than the mean of those not taking the drug. That means if you're taking it, the tumor is not growing as fast. Or hopefully it's shrinking. Okay, so what would a type 1 error be in the case of this problem?
But he says that the mean growth rate is less while taking the medicine, but it's not.
That's right. That's right. So a type 1 error would be to incorrectly conclude that the experimental drug is effective when really it's not. Now, as with everything in life, you probably can finish what I'm about to say. Our choices have what?
Rewards.
Rewards. Consequences. So what could be a consequence of this type 1 error?
People would have false hopes, people would buy it, and but they won't find results, so therefore they're suing.
Yeah, that could.
Or like people prescribe it, but like it may actually just make things worse.
Yep. So both of those kind of tie back to the whole The company could devote resources because they tell people, oh yeah, it's effective, so they're going to tie up resources developing this drug, sending it out to consumers. Yeah, it's really not effective. They could get sued, which then they'd be out even more money. I mean, they're tying up all their resources on something that's not good. Now let's flip the table. What would a type 2 error be?
The medicine works, but they still aren't convinced that it works.
That's right. That's right. So they'll conclude the drug is ineffective, but really it works. It's doing what it's supposed to.
The consequence of that would be multiplied cancer.
Yeah. Consequence of that could be the company would abandon the drug, but yet the drug was effective. Which means more people wouldn't get treated. Questions on this example? What do y'all think so far based on what we're doing? Is this about the same as yesterday or a little bit more thought intensive?
Slightly more
Gotta think a little bit more. It's not quite as automatic as yesterday's was. But at least we don't have to do any math. Easy math days today. If you want to call it that. Are we going to start math in this chapter Monday?
What is it again, the 13th of November?
Something like that.
We got a couple weeks.
Maybe it was the 16th. I don't remember. It's that week, but I think it's the Tuesday before Thanksgiving. Like before the week of Thanksgiving, not right before it.
I'm so ready.
I'm ready to get out of town for a week.
Where you going?
Fredericksburg.
Oh, all the way in?
I have an aunt that lives there.
Nice. That's a ways out there. I've never been.
7-hour drive.
I remember my parents went to Fredericksburg one time, and they called us and said that my aunt had to go to the ER because they were trying to open cans the country way, and she tried to do it and nearly sliced her thumb off with the edge of the can.
Yikes. Okay. So let's talk about the relationship between alpha and beta. Because as we just saw in that last example, our errors have consequences. So theoretically, would we want to just try to have no error? Yeah, we would. Let's just have no error. Everybody be happy, happy, joy, joy. And live the good life. But this is impossible to achieve because we must base our decision on sample data. We have to base our decision on sample data. And what have we learned about sample data? It does what? What? the data, the raw data itself may not have errors per se, but it moves around, it varies. So the sample data kind of varies. So it's impossible to eliminate error. So standard testing procedures allow us to select an alpha, which is our significance level of the test, but we don't have any direct control over beta. Well, I mean, we can control alpha, but we can't control beta. So beta is our probability of a type 2 error. We can control alpha, but we can't control beta. So if we select a significance level of alpha is 0.05, that results in a test procedure if we use it over and over and over with different samples. That means we'll reject a true null hypothesis about 5 times in 100. So that's what that alpha will give us. So why not always, if that's the case, if we can control alpha, why don't we just choose a really small alpha, and then we're less likely to create a type 1 error. Because isn't 1 out of 100 better than 5 out of 100? No. But with everything else held constant, if we decrease one type of error, it causes the other type to increase. So we're kind of in a catch-22 here. Darn if you do, darn if you don't. I'm sure it's not. That's the G-rated version of the quote. So the only way to decrease both types of error simultaneously is to increase our sample size. Jack the sample size way up there, then your errors will decrease. So no matter what decision is reached, there's always going to be the risk of having one of these errors occur. And just another analogy to use, think of it like, okay, you're the best driver in the world. Let's just think for a second. You're the best driver in the world. You've never had accidents. You follow the speed limit exactly. If it's 50, you're driving 50, not 50.1.
78.
Not 78. If it says 50, you're driving 50. If the light's red, you stop. If it's turning yellow, you slow down, not speed up to beat the red light.
Okay, I do that.
Okay, so you're the safest driver. But the minute you get behind the wheel, what do you still have a chance of occurring? An accident.
Because you can't account for the other person.
You can't account for the other person, yeah. But still, I mean, yeah. So error, we always stand a chance of error. All it takes is one slip up, even if you're the safest driver. It just takes one mess up for you to crash.
The insurance company was yours.
Exactly. That's what happened to me. Well, I didn't get my rates raised. Another person would have, but she never returned the insurance company's calls, so my repair never got made.
What, the other person that injured her?
Yep, I was in, I think this was last year, I was in Walmart, or coming out of Walmart, and I had turned the corner and was waiting for someone to back out of a parking spot close to the end of one of the aisles. And this lady just jumps in her car and throws it in reverse. I'm sitting there on the phone with my mom. I have a hands-free Bluetooth speaker, so I'm sitting there talking to her, and I see her reverse lights come on. I'm like, okay, she's putting it in reverse. She'll see me. No, the reverse lights come on, and she starts coming towards me, so I just lay on the horn. Of course, my mom's like, my gosh, what's going on? She can hear the horn through the speaker. I said, that's when I'm like, crap. So what just happened? Someone just backed into me at Walmart. So I get out and go up to her. Actually, I don't get out. She gets out. I stay in my car. She gets out and comes, knocks on my window. You need to watch where you're going. I was moving, and you pulled right behind me. No, ma'am. I was stopped the whole time I watched you get in your car and put it in reverse. No one was behind me. I have a reverse camera, and it catches everything. I can pull the recording if you want me to. Exactly. Exactly. No, ma'am. So I pulled up thinking I'm doing good, I'm getting out of the way. And my dad got on the phone right after that. He's like, okay, make sure you get her insurance, get her license number, and we'll just follow it on insurance. Well, she didn't want to give any of that to me because it wasn't her fault, it was my fault, according to her. And so he's like, no. If she won't give it to you, call the police and get the police involved. And so I repeated what he said, and she runs back to her car, gets her insurance card here. I wrote it down, said, do you have your license? I'm not giving you that. So, well, that's okay then, we can wait on the police. I'm not giving you that, I shouldn't have even given you what I gave you. You need to watch where you're going and have a nice day. She gets in her car and leaves. Doesn't wait for the police. Of course, it's private property, so the police get there, they take a report. And then they try to contact her to get her side of the story. She won't return their calls. And so then I file it on her insurance, since I have her insurance info. They try to contact her. She won't return their calls. They send her a letter. She still can't contact them. So finally the insurance company says, since we only have your side, we can't pay the claim, sorry. We're closing your case. Oh, lovely. So my car is damaged.
When was this?
A year and a half ago.
So what I'm hearing is, don't answer. You know, assuming they didn't get your, like, assuming the police aren't gonna come looking for you.
Well, being that it was on private property, the police aren't really pushing it.
I thought it was a Walmart.
It was, but that's still considered property.
Walmart?
Roadways.
I got you.
And Walmart, for whatever reason, supposedly they tried to get the security camera footage from Walmart, and Walmart wouldn't release it to them. So, I don't know. Anyways, let's do this little. This next little part's not on your notes, but just kind of do the thought experiment with me for a second. Let's consider the following hypotheses. The first one is that P equals 0.5. Or in the case of dual credit, P is greater than or equal to 0.5. No, not greater than. That's our null is greater than. Our alternative is greater than. It needs to be less than for dual credit. Okay. So this is the normal curve. It represents the sampling distribution for P hat when the null is true. So our mean here is at 0.5. Notice if I draw a straight line up, it goes through the high point. Wrong way. So the part of the curve that represents a type 1 error is this part in red down here. That part in red is a type 1 error if alpha is 0.05. And notice, this will help dual credit on a couple of questions on your assignment. Notice that since we have strictly greater than here, so we said yesterday that's a one-tailed test, right? Greater than, what tail is it in over here? The right tail. So the direction of our inequality points to the tail that we're looking at. Now that we're to say not equal to, then both tails would be shaded.
You said so it's less than or no?
If it's less than, it'll be on the left tail. Not equal to would be in both tails.
That's the two-tailed.
That's the two-tailed one, yep. That's why we call them two tails, because it takes into account areas in both tails. Okay, so that red area is the part of the curve that's a type 1 error. If the null hypothesis is false, and the alternative is true, then the true proportion is believed to be greater than 0.5. So the curve should really be shifted to the right. So we're saying that the alternative is really the case, which means our mean needs to be shifted over to account for it. Well, you see this piece of our new curve that's not shaded in right here? That's going to be our type 2 error. So that blue part would be the type 2 data. If we look, they both look decently sized. They look about the same. But now let's change alpha to 0.01. So now look how small the red is, the type 1 error, when we change alpha to 0.01. Red is a lot smaller. We're going to go through the same process. We're going to say, okay, we need to reject. It's really bigger. So we reject. Wrong way. So we move it over. But then what happens to the blue piece? Red got smaller, but blue got bigger. Wah, wah, wah.
If you mess with one of the areas, the other one gets bigger.
That's right. You decrease one, you increase the other. As alpha got smaller, beta got larger. So with that being said, we're kind of stuck here. Which error do I go after? How can I decide what alpha I need to use? Well, After assessing the consequences of the type 1 and type 2 errors, we want to identify the largest alpha that's tolerable for the problem. This is a typo right here. It's in your notes too. For everyone, this is a typo for everybody. This should not say 0.5. We're missing a 0 here. 0.05. The largest alpha we typically use is 0.05. Then we employ a test procedure that uses the maximum acceptable value rather than anything smaller as the level of significance. Typically, we do 0.05 as our alpha. If you think back to when we were doing, when we were talking about rare values or extremely rare values, what did we say a rare value was? If the probability was what? Less than 0.05. Yep. That was a rare value. Here comes that 0.05 again. That's our alpha, is what that is. We're tying that all together. So if we use a smaller alpha, though, we increase beta. Let's look at our last example. The EPA has adopted what's known as the lead and copper rule, which defines drinking water as unsafe if the concentration of lead is 15 parts per billion or greater, or if the concentration of copper is 1.3 parts per billion or greater. So the manager of the community water system might use lead level measurements from a sample of water specimens to test the following. So his hypotheses are that mu equals 15. Actually, if you're dual credit, this would be m is greater than or equal to 15. Versus the alternative of mu being less than 15. So notice this means that the water is safe to drink. Because if it's greater, then it's unsafe. We want to make sure it's safe. So this means safe to drink. Okay, so what would our type 1 error be in the context of our problem here? That's right. That's exactly right. The type 1 error leads to the conclusion that the water source meets the standards when really it's unsafe. So what's the consequence of this error? People die of lead poisoning? What were you saying, Nate? Lead poisoning? Yeah. There's possible health risk to the community. People could die of lead poisoning. And what about the type 2 error? What would a type 2 error be? Well, what's the error itself? Another consequence. What's the error itself?
They say it doesn't meet the requirements, but it actually does.
But it doesn't meet the requirements, but it actually does. What could be a consequence of this kind of error? Well, I mean,
I think the outsource water.
no, we have to outsource water. We're not going to go quite that extreme, Will.
Yeah.
I don't think the city's going to let everyone die of dehydration. They're going to have to outsource their water, and they could lose a good water source and pay more money in the process. So then they're losing more money. So then we have to ask ourselves, which one is the worst of the two? Type 1. You're killing people on that one. You're killing me, Smalls.
You said that one's better?
That's the worst of the two errors.
Yeah, okay, I thought you said better.
It's the worst of the two errors. So that's the one we want to control in this case. It's the baddest one, which means we need to control it. So since most people will consider type 1 error more serious, we want to keep alpha small. So we need to select a smaller significance level of alpha being 0.01. Remember, we can still make a type 2 error, but I think I'd rather them change water sources than have a bunch of people die. Blood poisoning. Okay, any questions on today? Yes.
So like, you know, those the big old meth poisoning in that. I don't know for that.
Flint, Michigan?
Yeah. How does that happen? Okay.
I don't know exactly how that happened. I know they weren't closely monitoring it.
I heard it was in pipelines.
Pipelines, that could be it too. Yeah. And then, so that compared with not monitoring, it just kind of snowballed to get where it was at. Yep.
I actually heard it's for being pregnant and running in the blood.
Yep. Yep. There's pretty serious stuff.
I go when he comes back.
I think they're still facing implications from that plant crisis. Every now and then I'll still hear something on the news about it.